Hey everyone, my name is Aaron Buchwald, and I'm a software engineer at Ava Labs, where I lead the development for Core ETH, the virtual machine that powers the Avalanche C-chain, as well as Subnet EVM, which is the VM that most people are using today in order to power their EVM subnets. So today I'm going to be talking to you guys about customizing the EVM with stateful precompiles on Avalanche. This is a really powerful notion that I'm personally extremely excited about. It's something that I use all the time and I can't stop talking about. And the reason this is so cool is that, actually let me go to the next slide. First of all, I'll start out with, actually this might be a little bit basic for this audience, but what is a blockchain, what's a VM, and what's a subnet? Everyone here is familiar with what a blockchain is, of course, but one thing you may not be familiar with if you don't have any experience with Avalanche is, what is a subnet? So a subnet is the idea that instead of running your application on the main chain, you might benefit from moving your application to your own chain where there is no competition for transactions to go through against other transactions on different applications. If you're launching an application on, for example, the Avalanche C-chain, and you want that application to have extremely low fees, it might experience much higher fees because there are going to be a huge number of DeFi applications running on the C-chain, which are highly competitive if there are large arbitrage opportunities. So if you're launching, let's say, a game on Avalanche, if you launch on the C-chain, there will always be these other profitable opportunities that lead to people wanting to issue transactions, and it's always going to drive prices up a little bit. So one way around that is that you can actually launch on your own subnet where there is no such competition, and you can offer your users significantly lower fees and significantly higher performance. Once you start to do that, where you're running your own subnet, where you're running your own blockchain, suddenly you can do a lot more interesting things. If you're running your own blockchain, you're running your own virtual machine, and so you don't necessarily need to run the exact same virtual machine that the Avalanche C-chain is using. So instead what you can use is you can use Subnet EVM, and we're trying to make this into the perfect playground to build any type of EVM application that you might want. And we want to make this into a system where you can hook up different plug-and-play modules to customize the EVM in whatever way that you want. So that is what the Subnet EVM is, and the way that we're starting with this is with stateful precompiles. The idea is that instead of simply running a smart contract application that just runs on the existing EVM, you might want to improve the performance of that. And so the way that we do this is we build on a notion that has existed in the EVM since the Ethereum Yellow Paper. The first instance of this is a precompile, and the idea that you can see here is that it's used to implement the SHA-256 hash in the EVM. The Ethereum Yellow Paper kind of lays out how these work, and the idea is that if you want to implement some complex cryptographic functionality, you probably don't want to do that in a Solidity contract. It's going to run on top of the EVM interpreter and be significantly more expensive. And so anytime you have expensive interaction, if you can move that instead of being on top of the EVM interpreter and something that you implement in Solidity, to instead run within the interpreter itself, then instead of running on top of the interpreter, it'll be running in the native language implementing the EVM interpreter. And because of that, it'll be significantly more performant and more efficient, and you can charge a much lower gas cost. So one example of this is for the SHA-256 hash, if you wanted to implement this within Solidity, you would have to do all of the math operations necessary in a Solidity contract, which would be both error-prone. You'd have to re-implement this library, but instead what they do is they use existing libraries in every single language that the EVM is implemented in. And by doing that, it's a much more standard process, and it's significantly more performant because it actually compiles down and runs in the native Golang in the case of Go Ethereum. And the way that this works under the hood is that there is actually just a pre-specified address that you call in the same way that you would call a normal smart contract, and you specify which address in order to specify which operation you want to use. So for example, SHA-256 hash would just be one address, and then you pass in the call data in the same way that you would pass in call data when invoking a smart contract. After that, under the hood, the smart contract will check how much gas is going to be consumed by that operation, and in this case, use the native SHA-256 library in order to return the result correctly. And so if you wanted to perform a SHA-256 hash, instead of having to implement that in Solidity, which you can do because of the functionality offered by precompiles, is you can actually just use the SHA-256 keyword, which under the hood is going to do this process of passing in the input data and calling that pre-specified address. So this is an incredibly powerful notion that has been used in the EVM to implement a number of different cryptographic functionalities, which would be much more expensive if you wanted to implement it on top of the EVM. But once you get to a point where you're starting to customize the EVM, it actually offers an incredibly powerful interface to build new types of applications, to add whatever customizations that you might want. And because this is the native to the EVM, it's actually relatively easy to improve the interface of the EVM and hook up whatever contract that you might want in that exact same language. And so we can actually create a precompile which will essentially pretend to be a smart contract implemented in Solidity. So for developers that want to offer significantly higher performance, you can implement your contract in Golang by implementing this simple interface. And what this is going to do is, under the hood, it's going to charge gas in the same way that the EVM does, and it's also going to implement whatever functionality using some pre-specified or some input specified by the user. And so using this, what we can actually do is we can behave exactly like a smart contract. So how does that work under the hood? Well, first of all, like, people may ask, what is this? What is a VM? What is Avalanche? And what is a VM? What can a stateful precompile be? And the answer is you can literally program anything. In the same way that the EVM provides a Turing-complete virtual machine, a stateful precompile is actually even more powerful because you can implement it in Golang or any other programming language, really. And that is obviously also a Turing-complete language, so you can implement whatever functionality that you want. Normally, you're actually limited by following the rules of the EVM. For example, if you are implementing a smart contract, you obviously can't mint the native token of that smart contract. It's a permissionless system, so you obviously can't send some transaction that makes it so some other address is no longer allowed to interact with the EVM at all. But if you're programming a stateful precompile, because it's under the hood in the EVM itself, you can actually program in different ways to break the rules of the EVM. So whereas normally a smart contract has to obey all of these rules, a stateful precompile, because it's actually built into the EVM interpreter itself, can break them in whatever ways that it wants, which is an incredibly powerful notion and also one that's very, very dangerous. So what does this look like under the hood? When you implement a smart contract, or rather when you call a smart contract, what actually happens is there's either a fallback function where there is no input or there's no function selector, or if you're calling a specific function on a smart contract, let's say swap token for token, then what actually happens under the hood is there's a hash that's taken of the function signature, and the first 4 bytes are used to determine, or are used as the first 4 bytes of the call data, so that a Solidity contract can, under the hood, use those 4 bytes to jump to the correct location in the code and figure out what function is intended to be called. So with precompilers, normally there is no function selector, but with this interface, what we've done is we've said, all right, if you're implementing a stateful precompile, you probably want to interact with it in the exact same way as if you were implementing an EVM smart contract. And so what we do is we actually say, all right, we're going to use a function selector in that exact same way so that you can actually just implement a Solidity interface, like so. So you can just implement this Solidity interface and say, hey, these are the functions that I want to call. These are the functions that I want to make available. And this stateful precompile generation tool can actually take all of these function signatures and generate exactly what their function selector will be, and then generate function stubs within the subnet EVM code base on your behalf, so that you can then realize, all right, these are the function stubs that I have to implement, and then you can implement arbitrary code in Golang to implement these functions however you might want. So this one in particular, this is one that I've wanted somebody to implement for a long time because I think it would be very, very cool. But the idea is here, you could provide a stateless storage interface, and so you can just write up this interface like so in Solidity. But if you wanted to implement a stateless storage interface using, let's say, for example, a Merkle tree, it would actually be very, very difficult and very, very expensive to do that on top of Solidity. So instead of doing that, what you can do is you can actually use the Golang code that already exists. And in the exact same way that the SHA-256 precompile leverages the already existing code, being the SHA-256 hashing library, in order to implement its functionality, you could even use the TriDB database code that is already implemented in subnet EVM coming from Go Ethereum project in order to implement the same functionality. And so just by using this existing library, you could actually implement and expose a Merkle tree interface to a smart contract. And so the question then is, why is this potentially interesting? For me, I see this as potentially interesting because on the long-term roadmap of Ethereum, one thing that people have been very interested in for a long time is to offer a stateless client. So a stateless client would essentially work by changing the requirements of a node from storing the entire Merkle tree to instead storing only the root of that Merkle tree. And then when it needs to perform operations on the values in the tree database, it would require a proof of the key value pairs that it actually interacts with. And by doing that, you can receive a proof of all the key value pairs that you interact with and update the root after the execution of that block. And this is incredibly powerful because it means that we can actually offer scalable storage on the EVM by moving all of that storage off-chain, or at least not requiring every single node in the network to have that complete storage, because right now that is sort of the largest bottleneck. So the idea with a stateless client would be instead you're going to switch to only storing the root. And for smart contracts that exist today, this is sort of a far-off goal that they can't currently use. But one way to get around that would be if you could implement smart contracts or storage for smart contracts using that exact same model. And the idea would be if you have a Merkle tree database where you want to store some arbitrary number of key value pairs, normally you have to store that in the EVM and pay an exorbitant amount for the storage that's required. Instead, what you can do is you can say, I'm going to use that exact same notion from the idea of a stateless client and use a Merkle tree directly in your smart contract to offer scalable storage while actually only storing a single state root on chain. By doing this, you can offer significantly more scalable storage, all by using that one native library that already exists. So this is one project that I'm particularly excited about, that I think would be very, very interesting and cool to see somebody implement using subnet EVM. But broader than that, this is just kind of a notion that you can implement anything using a stateful precompile and move functionality that currently is implemented in Solidity or functionality that currently cannot be implemented in Solidity because you want to change the rules of the EVM or modify your contract in some way or your virtual machine in some way. This is a powerful tool to do that. And when you go to interact with it, it'll behave exactly as if you were interacting with a normal smart contract. Thank you.
Thank you very much, Aaron Buchwald. Thank you for that presentation, and sorry about my ignorance about your last name. I thought that it was Buchwald, but thank you for correcting me. We do have a couple of questions for you, so here's the first question. Among the Avalanche subnets, what's the most representative subnet?
That's a hard question. I would say that there is no answer to that. You know, the idea with a subnet is that you can build any application that you want on it. So there's no one subnet that is the only functionality or representative, so to say. Right now, the most popular use case is for on-chain gaming. And the reason for that is that there's a very large demand for block space by these on-chain games. But if they're implemented on either Ethereum or the Avalanche C-chain, then they're going to eat up a large amount of block space, and they may not actually want to do that. They may not want to charge their users the fees that go along with that. Additionally, games are usually sort of isolated ecosystems, not entirely, but they can do with some amount of isolation. Where for games, it's really okay if they're not directly on the exact same chain as all of the different aspects of decentralized finance. So games are a really, really good use case because you can run it on a chain, on your own chain, be completely isolated, and you can move assets off-chain as necessary, but it's not important to the game itself to be able to, in a single transaction, interact with the game, move an asset through another contract, perform a flash loan, and then perform some number of different arbitrage operations. So games really can exist in isolation very, very well. So I wouldn't say that they're representative, but it's a very good and very natural use case. One thing that doesn't necessarily work as well is, let's say, if you wanted to launch a flash loan product. A flash loan is only as useful as all of the other aspects of decentralized finance are present on the same chain. If you want to take out a flash loan, you want to obviously immediately use that to perform some operations in the world of DeFi. So an application like that, you really want to run on the Avalanche C chain where all of those DeFi applications exist. Anything that doesn't require that level of interoperability, that level of composability, can be moved to an Avalanche subnet at very little cost in terms of what it's giving up and where that application lives, and gain a huge number of benefits in terms of significantly more block space, offering significantly lower fees, and much higher performance than if it were just running on the Avalanche C chain.
Thank you for that detailed answer. I believe that we have another question. What are the limitations or downsides of utilizing subnets instead of a C chain?
Yeah, I think most people who are migrating to subnets or similar types of projects today are coming from the world of launching and running their own decentralized applications. So right now, these people, they are running a decentralized application, usually a very successful one, and they're familiar with the challenges that come with that. So whether it's Solidity or the front-end website that goes with it, interacting with wallets, et cetera. But the skills required to run a subnet are very, very different. And so if you're just running an application on a C chain, you don't have to worry about or deal with these things at all. The moment that you move to a subnet, you are actually operating your own layer 1 network, essentially. So once you're doing that, that means that you have to run the validators, make sure that they stay up, and make sure that they are sufficiently performant, that they meet all of the requirements. And this is the challenge that's very, very unfamiliar to most developers who are coming from the world of building smart contracts. So I would say that challenge is something that's unfamiliar, it's much more difficult, and that's probably the biggest downside, is the additional complexity that comes with running a subnet instead of just running an application. And so I would say if you're running some application and you haven't proved it out yet, and you have never run your own subnet before, probably the best and easiest place to start is going to be running that initially on the C chain. And then as you kind of see that come to be successful, if you realize that you need to scale to a much larger degree, then it's probably time to think about moving to a subnet and take advantage of the scaling properties of that.
So do it consecutively then, by step?
Yeah.
All right. All right, then I hope that answered the questions. Please give another big round of applause to our speaker. Thank you very much, Aaron. Thank you. 네, 다시 큰 박수 부탁드리겠습니다.